Welcome to another video lecture on digital electronics. In this video, we'll be seeing what is a synchronous counter. So what we are designing is a 3-bit synchronous counter, and this is a up counter, which means it is going to count from 000 up to 111. So in this synchronous counter, you can have any sequence. It is not mandatory that you have to go from 0 to 1, 1 to 2, 2 to 3, and so on up to 7. We are designing this counter in a sequential manner, but in synchronous counter, it is absolutely fine to have a state from 1 to 3 to 2 to 4 and back to 1. That is possible. So what you have to do, the very first state is 000, and whatever is the next state you have to mention here. In our case, we are doing 0 to 7 in sequence, and hence I have written 1 here. Otherwise, say if this is 0th state and it is moving to 4th state, then I can easily have 000 written here, and I will have 100 written here. This is just an example to show you. So after 1 I am moving to 2, after 2 I am moving to 3, after 3 I am moving to 4, and so on. After 7 I am moving back to 000. So this is the present state and this is the next state of the counter. Now to get this kind of a counter, currently what we are using is a JK flip-flop. You can use any flip-flop of your choice. So since we are doing a 3-bit counter, of course I will read 3 JK flip-flops. So I have J0, K0, J1, K1 and J2, K2. Now depending on the value of Q2 and Q2 plus, I will check the excitation table to have 0 and to get a 0. What is the excitation of J2 and K2 that I should be using? So this you will find from here. See, I have a 0 and I need a 0, right? So I have a 0 and I need a 0. My JK should be 0x. See here, to have a 0 and to get a 0 in the next state, I should have 0x as J2 K2 as my excitation. Similarly, one more example, if I have 1 and I want a 0, if I have 1 and I want a 0, my excitation says I should have x1 and I have an x1 at J2 K2. So in this way, by looking at Q2 and Q2 plus, you will fill your J2 and K2. By looking at Q1 and Q1 plus, you will fill your J1 K1. And by looking at Q0 and Q0 plus, you will fill your J0 K0. Once this is done, then what you're supposed to do is use K maps. Since we are using a JK flip-flop, we will have 6 K maps, 1, 2, 3, 4, 5 and 6. Had this been a T flip-flop, then you will be having only 3, because you'll have T2, T1 and T0. So I'm also giving you a generalized idea simultaneously so that you can design a synchronous counter of any required state or any mod counter or any such counter using any of the flip-flops, right? Okay, so once this is done, then will you be using K maps to get the reduced form of the equation. So I'll have K map for all of these. I'll have 6 K maps here. So these are my K maps. This is for J0. What are my inputs going to be? Q2, Q1 and Q0. So my J0, since these are don't care conditions, I can consider this for grouping in a major group. So I have a 1 here. Similarly, I have K0 also as 1. Then we'll be solving for J1 and K1. I request you to solve this on your own to get the idea of how the answers will be. So then you have J1 K1 as Q0 and finally J2 K2 as Q1 into Q0. And the final step that you have to do is to design the counter. So first you will be making 3 flip-flops, J2 K2, J1 K1 and J0 K0. Now the inputs will be decided on the equations. So what does the equation say? J0 and K0 should be 1. So I have connected J0 and K0, J0 and K0 to 1, right? Okay, then I have J1 and K1, which is Q0. So I have J1 and K1, which is coming from Q0, and J1 and K1 both are coming from Q0. Okay, so second is also done. And the third one is J2 and K2 is equal to Q1 into Q0. So J2 and K2 both is equal to, I have an AND gate here. What I am multiplying in AND gate? I am multiplying Q0 and I am multiplying Q1 from here. So this becomes my J2, K2. That's it. All those connections. And one final thing, since this is a synchronous counter, all the clock pulse of all the flip-flop will be simultaneously going from this line. That's the only designing part. So I hope the video is understood. Thank you for watching.